Let's continue look at on the particulate formation and abundance on the premise frame. We turn to the page of 4.7 from our lecture notes. If you look at the premise frame, because in the premise frame, usually the fuel will mix with oxygen, where therefore the formation and the burning of the soot, the carbon particle, basically is depend on the local temperature and mixture ratio conditions, as described here. For example, for carbon, okay, carbon burning. If you have a strong carbon burning in premise frame, that means you may not have a soot formation, which means the carbon burning depends on three major parameters. One is the temperature, and the other is the residence time, and the third one is oxygen. If these three parameters high enough or long enough, large enough, then you will do have a strong carbon burning. For example, for temperature is high, then actually they will promote the chemical reaction for carbon with oxygen. Then the carbon formation cannot be uh, enhanced. And if you increase the residence times, then the carbon will be oxidized completely. And if you have if you can in the lean conditions, you have enough oxygens, then the carbon burning will be will be more complete. Which means when you look at the molecular structure for different kinds of fuel, actually those kinds of subformations that depend on directly on the reactivity of the fuel with oxygen by this series. Actually, the naphthalene is has a much potential to produce the soot, but ethylene has less one. Okay, and usually from the frame structure, as we described earlier, you may see the soot usually form near the ridge limit for methane, ethane, propane, and butane, because these four fuel, hydrocarbon fuel, actually they has less molecular weight, and the carbon hydrogen ratio is not too much. Which means you can have a soot only uh, in very rich condition, very close to the rich from the limit. Okay, and the rich limit means if you increase the fuel more, then you may not have a frame exist for premixtures because it's too rich. Okay, and it means for these four hydrocarbon fuels, it is very hard to have a strong soot formation unless you go to the very rich condition. Okay. From our experiment, when you generate a planar premix frame, for example, like this, you have an unburnt premixture supplied from the loader burner, and you can generate, for example, you have a stagnation point flow, and in this stagnation point flow, you will generate a planar premix frame, and you try to make the burning be more rich. Okay, in this case, from the observation in our previous experimental results, you can see there is a blue flame occurs here usually. Okay, blue flame is exists in the front of the oval of yellow flames. There is a blue flame, and between the blue flame and the yellow colored zones, there is a dark zones. And usually, if you do the measurement from the GC or from the laser diagnostic, and you can find out in this dark zone, you may have a high concentration of this species, as I list here. And after that, in the downstream of the dark zone, then you will find out there is a yellow yellow carbon zone. That means that there is a soot layer. Soot layer always exists behind of the blue flame, okay, for a rich hydrocarbon flame. And if you further to look at some physical parameter, and you find out the pressure has some influence on the soot formation for diffusion fan and premise fan. If you increase the pressure for diffusion fan, usually the soot will be increased. You understand the soot formation occurs in the fuel side of the diffusion fan, which means that in the region of rich fuel region, in the fuel sites, there is they do not have too much. Actually, they don't have the oxygen. Therefore, if you increase pressure, that means that you increase the interaction rate between the subparticle, and then they have a big chance to make bigger and bigger. Agglomeration become more possible for the growth of soot. Okay, but for premise frame, depends on the situation. The threshold for the first appearance of soot does not vary very much with pressure, because the initiation of soot formation for premise frame actually is governed by the mixing ratio, okay, and also the temperature. Pressure may not be the important one, but if you do have a carbon formed set free, then the pressure increase will give you the chance to increase the soot formation. Okay, and the preheating of your premise gases, actually they will increase the overall temperatures. Then you will shift the threshold for soot formation to slightly richer premixture. That means the preheating of premise gases is will suppress the soot formation. Okay. Now, if you increase the flow rate of premature, actually, when you increase the flow rate of premature, that means that you reduce the residence time. You reduce the residence, and at the same time, you may increase the flame temperature, because you input more fuel into your combustor. The chemical reaction become the heat release become more large for a given control volume. When temperature increase, these two factors, temperature increase and the residence size reduce. That means the soot may not easier to be formed. Then you will shift the threshold for soot formation for premise frame. But near the threshold condition, this is very important. You need to understand near the threshold conditions, the temperature is a key factor, because they will enhance the oxidation process. Okay, but for very rich, the temperature become high, then they will promote the soot formation. Okay, for rich side, you do not have enough oxygen. Okay, when temperature high, cannot help the oxidation of soot. And but they promote the carbon, the hydrocarbon fuel decomposition, and they produce more soot. Okay, which they tell you in different kinds of situation. For example, different kind of mixing ratio. Under a threshold condition, high temperature is good for reduction of soot, but for rich condition, high temperature will help the soot formation. Sometimes you figure out just a few literature give you the result. Electric fields, if you can provide the positive ions, and those ions will have the growth of carbon particles. And there is also some interesting results from the previous experiment work. By adding additives, and then you will give a different kinds of results. Let's see if you apply the SO3 into premise vent and diffusion, when you find out they will have a different kinds of results. And I hope you remember, as we described earlier, in the combustion process, there is a three important active species: hydrogen and OH radical and oxygen radical. These three radicals are most important parameters species to promote the multi-step chemical reaction through the branching chain reaction, right? And these three radicals are quite important. And but if you look at the influence coming from the SO3 additives, you can find out if you put into the fuel side of your diffusion frame, then the SO3 will react with hydrogen and to become OH. Then now you find out there is the oxygen occurs, but this oxygen coming from the SO3, and this OH radical will have oxidation, then the soot will be suppressed. Okay, will be suppressed. This is the inference coming from the SO3 on the fuel side. But however, if you put this SO3 species into the premise frame, they will go through these two reactions. These two reactions show you will absorb the oxygen, you will change the active oxygen species to O2 and H absorbed by the as HSO2. Okay, that means that you remove the O and H radicals, and this will prevent oxidations of soot. Then the soot formation will be suppressed. There is the experimental result tell you if just add a 0.2% SO3 in isobutane air frames, then the soot will be increased by 40%, which means that when you look at this, the influence coming from SO3 on diffusion frame and the premise frame, actually they play different kinds of role. Depends on the chemical reaction you may have for the fuel side on diffusion frame and for the premise frame. And additionally, there is some, you can add some salts, for example, sodium and lithium and cation, those kinds of salts, actually they will shift the soot formations to the more rich side. That means that they have a strong inhibitions on soot formation. The chemical reaction rate a chemical reaction occurs like this way. The lithium, for example, for the lithium, react with the water, then they will provide the hydrogen radicals, and also later the next chemical reaction will produce the OH radical. H and the OH radicals have oxidation, then they can suppress the soot formation. Okay, but there is an exception for variant. But variant, they first reduce the soot to a minimum value, but then increase soot formations. Okay, depends on the condition you may have, especially for the emission ratio. Okay. Now let's look at the influence on the formation of the particles, particulate of the. Later on, I will give you the picture to show the so-called coal from liquid hydrogen, liquid hydrocarbon pyrolysis. That means we are looking more. We are looking at more closer to the irregular injection through the spray atomization process. And if you usually in our previous discussion, we are more focusing on the soot formations in the gas phase, right? And in the gas phase, actually the soot formation occurs initially starting from the decomposition of your hydrocarbon fuel. Then they will release carbon carbon atoms out, and the carbon atoms they can collect together to nucleate carbon particles in this process. But for the hydrocarbon liquid fuels, if you have a liquid spray impinging directly on a very hot ore, okay, now they will experience the so-called liquid phase cracking and goes through the pyrolysis. Finally, they will release the hydrogen out, then they will produce a so-called coking. Then the liquid phase cracking will follow by this way from the paraffins, okay, liquid phase, then often continuously and go through these procedures to becomes a carboid coke. And in this process, actually, they release the light hydrogen radical out, and all the carbon will be remained and it becomes a solid on the surface of your high temperature of the high temperature surface of your combustion chamber. And usually the fuels always contains anomalies from the petroleum coke more readily from than other fuels. Okay, and I let me change the presentation file to the PowerPoint to let you know the observation from the real application. Yeah, there is some photos to show you what is the coking or deposit. This figure actually taken from our experiment. At that time, we used different kinds of liquid sprays impinging to the horizontal combustors, and after for operation for long times, and we open it and find out we have a big black solid materials and attached to the burner exit. Okay, and this is when you bring this out. This is basically an example for the deposit of the heavy fuel oil. Okay, since you have injections, and sometimes the spray may not have a good atomization. Those liquid fuel will attach to the burner head, and since the burner head has experienced a high temperature, and they will go through the, the, the the decomposition structures and the cracking and of your liquid fuel, and then finally you will have some coke attached to the burner exit. Okay. The other example, actually, we have the pictures from the so-called fire tube boiler used for a company. And when they open the door, the front door of the fire tube boiler, you can see those kinds of tubing has a very has uh, a black color, right? That means that in each tubing that contains a certain amount of deposit, and then those is a very thick and for example, for this one, for this deposit is very is like a solid. Okay, and this is a typical example for you to know what is the cooking. And you actually we did some experiment to check the deposit of your gas of the gasoline. I can show you. Sorry, I moved too fast. Okay, this is the experiment study on the deposit formations on a hot plate. And for example, this is a water cooling plate. We use water cooling in the other surface, and the other on the top surface, actually they will experience a spray burning. Okay, and the left hand side show you there's some deposit coming from the burning of gasoline flame, and the right hand side to tell you the deposit coming from the burning of the diesel spray. For the gasoline spray, actually, those kinds of spray burning, they already since the gasoline spray, the gasoline has a lower boiling point and easier to be to be gasified. Then for the spray frame, usually before the spray go through the spray frame, they already gasified, which means that in the environment of the downstream, the downstream of the premise frame, actually they only exist gas the carbon particles in the gas phase, and when those soot appearance occurrence, then will hit to the plate, then they will formed on the surface of the plate. and the distribution is very uniform, but basically they give you the idea. They just the attachment, the deposit of your solid particle, carbon particle on the on the plate. But for the diesel, they show you different categories for the deposit. At the surface, actually, you can see the liquid droplet, the liquid impinge onto the plate and the cracking on the surface. Okay, this is a complete different structures for the gasoline and the diesel. They tell you before the flow reaching on the cooling plate, the hot plate, then actually for gasoline, they were gasified at first, then they have some nucleation of carbon particle, then later on the carbon particle impinge on the surface of the plate, and they will become a more uniform and will nicely distribute on the plate. But for the diesel, actually they cannot finish the gasification of the diesel droplets. They still remain the liquid droplets, and then those liquid droplets impinge on the plate, and in a very short time they'll go through the cracking process. Then they will produce the coking on the plate. Okay, they are completely different. Okay, this is a example to let you know to have some experience on the behavior of coking through the liquid petroleum fuel. Now we go back to our lecture slides, and we will continue to look at because we finished the discussions on the soup formations, and we need to go to the next subsection to let you know how can we remove the particulates from our emission process. There is several equipment to be used. I will show you quickly. The first one, we call this as a mechanical collectors. Basically, they are those kinds of mechanical connectors was control or was operate based on the centrifugal inertia and the gravitation forces. Let me try to explain to you. If you look at these pictures, this is a typical one for the mechanical collectors. The dust latent gas actually coming from the combustion chamber flow through from the left hand side, and when they go to the move into the collectors, they will first they will flow downward. Okay, here they will flow downward, then reverse and flow upward through a spinning vent. By this change, the change of flow direction, actually, if you see this gas has some dust, right? There were some different diameters of particles latent in the flue gas, and by this change the flow directions, large particles will have an inertia and influenced by the gravitation force. They will fall down to the hooper. Okay, and those flow will continuous change the direction, then flow upward by go through the spinal vent to produce the centrifugal force, and this centrifugal force will additionally to that medium particle size of the droplet or particles to move to attach to the surface of your van, then they will fall down because they lost their inertias. And later on, the cleaner gas will continuously flow upward through the upper deck. Then the clean gas will flow out. Okay. By this flow arrangement, you will find out there is some inertia and a gravitation force acting on the float to let the larger particles fall down to the hooper, and later on they use a centrifugal force to push the medium particles to be attached to the surface of your van, and they will fall down because they lost their inertia, and those kinds of medium size of particle will be collect. But they still have a very tiny particles where will go flowing with the gas flow and moving out, which means that by using the mechanical collectors, then they just can remove only 92% of fly ash from the spreader stoker flue gas. Actually, spread stoker flue gas usually contains a large amount of particles, and for the mechanical collectors, they do not have a not too high efficiency. They just have a 92%. 8% of the fly ash, they may contain smaller particles, and they will flow out. But for the mechanical collectors, actually, the cost is less. Okay, it's only 1/8 that of an electrostatic precipitators or blackouts. But for the electrostatic precipitators and the backhouse has a higher efficiency for removing the particulates out. Now the next one we go to introduce the electrostatic precipitators (ESP). Okay, here they tell you the main functions like this. They use the correct. There is there's a two plate. Actually, we call this the correcting plate, but they can generate. And there is a electric plug. Okay, here there's a discharge electrodes. You have a discharge electrodes, then they will produce the electric field based on the conjunction of the plate with the electrode. Then you will produce the electric field. Then initially the particles of inside of your flue gas, they were in charge. When they have when those particles move into the region between these two plates, they will change their directions of flow and to attach to the collecting plate. And this tell you the dust particle, they will move along this path and to attach to the collecting plate. By this influence, the particle, the charged particles will move along, follow the electric field and attach to the plate. And for certain time for collections, then you can shake the collection plate to push to let your particles move downward. Okay, here they tell you you need to have a rating system. Then they will generate the vibration and cause the collected dust to fall into the hooper. Okay. And for this equipment, they can remove more than 99.9% of fly ash from the flue gas. And this is a very nice efficiency. Usually, large fire power plants, they were equipped by this ESP to remove the particulates completely out. Therefore, people usually believe there is the very small, only 0.1%, very tiny particles flow out through the chimney of the fire power plants. Okay, and here they tell you the proper sizing of precipitator is depends on the type of fresh air, especially for high sulfur contents has a low resistivity and require a small precipitator. Then I will tell you how it works and the influence on that. There's two different kinds of design. I skip it to not give you the detailed description, but I want to tell you how to arrange the those equipments for the flue gas. Okay, this is a typical example. Tell you if you have a higher sulfur content, for example, you are burning a coal, you use coal as a fuel for your furnace or your boilers. If you have a higher sulfurs, then you will find out the resistivity is distribution is something like this in the temperature range. Actually, they will have a higher resistivity in a larger temperature range. But if you increase the percentage from 1 to 3%, you will find out the resistivity becomes smaller, and they were the temperature range become a shorter, become a smaller. Okay, which means if you have a larger sulfur content, then you will have a high corrections on the soot particles. Okay, then usually people try to arrange their precipitators in very close to the boil outlet. Then we call this a so-called hot precipitations. Hot precipitation, that means that they will experience the flue gas with a high temperature. And the precipitator is located upstream of the boiler air heater and induced dry fan, because the flue gas will flow out through the boiler, then they will go to the air preheaters to have some preheating for the inlet air for the boiler. Then they will go through the induced draft fan to chimney and flow out. Okay, but they try to arrange the precipitator ahead of the both air heater and the ID fan, because they will experience the temperature is high, it's around 600 Fahrenheit, and they will sometimes they have more more efficient to carry out the soot particle. Since in this situation, the particles still contain certain amount of sulfur, because they do not go through the desulfurization. Or usually the desulfurization will put into the very downstream in the whole stream. Okay. So then, since the higher temperature will give you have a higher efficiency to collect those particles. For example, for this range, 450, when you go further, then that means the resistivity for your coal particles, the carbon particles, is almost near zero. They are easily to be correct. And this is good for us to look at the application, the operations of air heater and the induced draft fan. Since before the flue gas flow into the air heater and the ID fan, all the particulates, soot particle, be collected by the precipitator. Then the flow will just has the purely a gas flow. If you cannot remove those kinds of particulates, then those particulates, as I mentioned, they just like even their size are very small, but flow velocity will carry with them. Then they have a certain amount of momentum when they impinge onto the surface of air heater or the blade of the ID fan. They will produce some pitting and a corrosion problem. But sometimes if you need to, but well, for the hot precipitations has another problem you need to solve, because they put the precipitators more closer to the boiler exit. That means the flow has a higher velocity. The most important thing to consider precipitator depends on the flow time. Since you have a plate, right, and you need to have a residence time to let your particle be changed their directions to be attached to the surface of your plate. Okay, then the flow time, if you have a higher velocity, then you need to have a larger plate to accept the flow will reduce the velocity. Then later on they will attach to will be more attached to the surface. That means that for hot precipitations, you need to a larger size of the precipitator, and this will tell you if you want to use hot precipitations, then you need to have a large room or large space in the downstream, large space in the downstream of boiler to complete to have a more complete precipitations. Now, some people think about this may not be good choice, because you may not have enough room to produce, to generate or to build a large precipitator with the larger size of the collector plate. Then they try to use the small one. When you use the small one, that means that you need to, for example, in this case, here they tell you you may use the so-called co-precipitation. You move a little bit down in the downstream sides of your flow system. Then people try to introduce the SO3 or ammonia, those agents, and they will produce the lower resistivity, as I explained earlier. Okay, in this case, when you go to the lower temperature regions, then if you increase the sulfur contents, then you will reduce the resistivity of your particle, and then they will improve the efficiency for the corrections. Okay, this is some practical arrangement for the precipitations. Now the third one is still is a useful one. Is the big filter house, or we call it a big house or fabric filter. They still can have a high efficiency. They can remove more than 99.9% of fly ash from the flue gas, and prefer for the low sulfur content. Okay, we already emphasized precipitators is good for the low sulfur content, which means it's a more efficient, more likely to be used for the coal burning. But if you do not have the large amount of sulfur content, you may use the big filter house, big house. Okay, here this is the mechanism for different kinds of applications. For the big house, they have a so-called figure A represent the post-jet cleaning. The figure B represent the reverse air cleaning. Final one is the mechanical shaker cleaning. I give you the example to explain it. For the figure A, actually you can see the flue gas coming from the downstream, from the lower portion, and you can see there is the tube bag, and they show you two different functions. The left hand side show you the flue gas coming in, okay, and then go through this current. Actually, there is the flange, okay, but shown by a broken line, and you have a big surface attached to the flange, and the flue gas will flow through the filter, the back surface, then flow into the current, and those particles will be filtered out on the surface of your bags. Okay, and the clean air will go through this way. Okay, and flow out. This is a clean gas outlet. And the other one, actually, they are working on the clean process. Since you the left-hand side tell you that you will have some soot particle attached on the surface of your bag. Then the second steps, you will change your flow condition. Now you use the compressed air from the top part. There is the tube, the compressed air coming in and flow into the interior, interior of your tubing, and flowing outward through the filter surface. And by this flow motions, the clean air, compressed air, will push those deposit particle dropped to the hooper. Okay. Therefore, you may have a serious bag acting on the collection of your subparticle particulate particles, and then the other one is they just push out those kinds of deposit particles to fall down. Okay, by this way, then they can clean out all the particulates and then the clean gas moving out. Okay, and then the right hand side, the figure B, they tell you they are separate. Okay, and they use the very similar way. This figure tell you flue gas coming in and flow out, and the particulates will deposit on the surface of bag. And the right hand side, they go to the cleaner process, then they will have a compressed air move from the other way and push those kinds of deposit particles fall down. Okay, and last one they just shake, use the mechanical shaker to shake the bag, and those kinds of collected particle will fall down. And the most important thing there is the design for the efficiency to achieve the higher efficiency based on the air to close filtering ratio. Depends on how much flue gas you will have. Then you use the gas volume flow rate to divide by the bag surface. The typical design for the high efficiency, then they will this value will equal to 0.5 to 4 centimeter per second. Okay, and this is a typical arrangement for the reverse air fabric filter systems. And you can see this is another one to see there is the two different strengths, and the dirty air inlet and the clean air outlet, and then they use the shaker to shaking down the deposit particle to into the hooper. And this is some arrangement for the I think this is the this is just like a post jet. This like as I mentioned the figure A. Yeah, the post jet cleaning systems. Okay, this just can give you some understanding on the arrangement. Okay, the final one we call this the weight approach Venturia scrubber. Actually, for this scrubber is used for many classical or many old systems. They use the centrifugal force, inertial force, and also add the water for the scrubbing. Okay, here when you have a flue gas in, and here there is there is a scrubber. Here you have some water, because the water coming in tangentially, then they will produce a sorting around the surface of your scrubbing systems. And when you have a gas flow in, and the gas will have interaction with the water, and some particles, since they have some the weight, because the large droplet, large particulates has an inertia to closer to attach to the liquid surface, to the water surface, and to emerge into the water, and they will be carried out. In general, the pulverized fire coal with the fine particles require medium energy scrubber. The energy consumption for this scrubbing system is quite large, because you need to generate the higher flow rate for the water, and to have some the sorting motion, then you require a large amount of energy to produce it. In general, I think this is a very nice pictures to let you know how to use the different kinds of cleaning equipment to face different kinds of operation on removing the particulates for different applications. Here, the horizontal axis represents the size, the particle size you may have. From left hand side to the right hand side, the particle size increase continuously. Okay, and the upper part represent the particle generates from different application. For example, if for the carbon brake industry, they will produce some particle size range in this range. And for oil smoke in this range, actually they represent those particle size are quite small. Okay, and here even the diameter of gas molecule, you can put it as a comparisons. For our energy application, here there is the pulverized coal fly ash. They will exist around 100 micron, and lower than 1 micron, 1 to 100 micron in this range. Okay, and the cement dust, they will exist. They will has a higher molecule particle size from the 10 to 100. Okay, and pulverized coal even they will have a more larger particles exist even to the 500 micron, 35 micron, okay, 30, I'm sorry, 350 microns, and you can check the size of the carbon part, the particular particle made by different kinds of application, and you can figure out what kinds of cleaning equipment need to be fit, and to make it more efficient correction to remove the particles. For example, here, if you use the elastic EP systems, you will find out they will collect the molecule particle size from the 0.01 up to 10 micron, okay, for this range. And you will choose the fabric filter, the big house, and the range is around from the 0.1 micron up to very close to the 100 micron. And they can have efficiently to remove the particles for example, for the pulverized cold flash and the oil flame. Okay, and those mechanical correctors and web scrubber, actually they tell you they can have a good performance to remove the large particle size, but they do not have a good efficiency to remove the very tiny particulates, small particulates. And there is some comparisons on the key emission control devices. I think there is just a competitive result, and you think about how to choose it. For example, here, the in terms of the efficiency, you can see the filter, okay, and the precipitator, they have a higher efficiency. And if you want to use the scrubber, actually they can increase the efficiency a little bit higher, but they can reach the 98% for medium energy. If you do not use too much energy, that means that you reduce the supply of water, then the efficiency will become lower. And in terms of the pressure drop, because when you do those kinds of cleaning, then the flue gas goes through those equipment, they will produce a pressure drop. Then the other problem will occur because the flow cannot move smoothly out of the chimney. Then you can see the cyclone corrector, because they reverse the flow direction, produce a high pressure drop. Okay, but for the filter, they still have a high pressure drop. But for the precipitators, actually, they do not have some the change of size of your flow streams or directions. Then the pressure drop is the minimal one, and then you can let the flue gas still have a momentum to flow out through the chimney. Okay, and the gas velocities, they usually have some range. Okay, and this one for precipitators, actually they require the gas velocity a little bit larger. Okay, and since they always put in the location very close to the boiler, and they have a higher velocity. In terms of installation cost, definitely the figure house, the figure filter house and precipitator has the highest invest. Okay. In general, when you look at the consideration on selecting the emission control equipment, usually there's four key factors you need to consider. The first one, the property of your delivered fuel. If you burn the natural gas, actually you do not need to have those kinds of particular removing particular equipment, right? But if you have a coal, then you burn in the coal, then you need to have a big house of the ESP. And the second one is the size of boiler plants. This is very important. We just mentioned electrostatic precipitator are not generally recommended for the plants below 40,000 and up to the 50,000 pound per hour of steam, because the precipitators requires a large space, because they need to install the collecting plate and it depends on the flow velocity, or the velocity, flow velocity of the flue gas. Okay, but if your board plan is a small size, you don't need to use it. Maybe you can just use the big house. Okay. And the type of firing will influence the concentrations and the size of pollutants that reach the stack. Definitely, you understand from our previous analysis for different applications for pulverized coal, then they will produce the different the particle size range compared with the pulverized coal. That you need to choose different kinds of emission control devices. Okay. Finally, yeah, pollution control regulation must be known for the particular site. But for this this kinds of thinking, actually, the concept basically came from the very earlier 20, 30 years ago. But in nowadays, actually, those pollution control regulations are big. Most of them become very strict. That means that you need to try to prevent, try to remove all the pollutants out for the large amount or for the large power plants, because the regulation become more strict, and you need to follow. And you cannot say in this region you can have some flue gas without cleaning and moving out. Usually you need to have this sense. You need to try to remove all the pollutants out in different kinds of place. In different place. Okay. Okay, we finished the discussion on the particulates. Now, next one, we will move to the introductions on the nitrogen oxides.